So in this video, I'd like to show you how to compute this integral in two ways, the harder one and the easier one. So the typical way that is shown in a standard calculus course is using integration by parts. So we can choose this function to be, say, u, and this we would choose, maybe we would choose this one as u and this one as v prime, because this one is easier to integrate, right? It's just the same, but nevertheless. Okay, so let's go. So this is going to be uv. So, and the integral of v is, of course, it's just the integration of e to the power of alpha x. It's just 1 over alpha e to the power of alpha x. We can see easily that if we differentiate this function, then we get e to the power of alpha x. So it's going to be uv. So it's going to be sine of beta x, this. And then we need to subtract the integral of u of v, which is 1 over alpha e to the power of alpha x. And here we would have to compute b u prime. So it's going to be beta here. And the integral in the derivative of sine is the cosine. So it's going to be cosine beta x dx. So that's the integral that we need to compute. So we started with this. So that's the integral that we need to compute. So if we rewrite this, this is 1 over alpha e to the power of alpha x. And here we'll have sine of beta x, and here minus beta over alpha, and here we need to compute the integral of e to the power of alpha x cosine beta x dx. So actually we'll see that, computing this integral, which we called I, actually allows us to compute its companion integral, which is this one. And we'll see that this occurrence of the cosine is not a coincidence. In fact, there is a reason for this to appear, but all in a few moments. So now, again, we need to compute this integral, which seems just as hard as this one, as the original. And so now we have to proceed here, and still we would try to integrate this by parts, but we have to be careful, because if we will make, say, the wrong choice, so for example, if we'll choose this time, for example, this function, this to be u, and this we'll choose to be as, again, if we'll switch them. So if this is going to be, say, u, and this is going to be v prime, right? Then what will happen is that when we integrate this, we'll actually return to the same integral. So we have to be consistent in our choice here. And so since we chose v prime previously to be this one, we have to be consistent here, because the other choice will lead us to the identity that I equals I. So, and that's not very helpful. So we have to be, that's the hard part here, that we need to stick with the choices that we've made, because when we integrate this by parts, then there is a choice for u and v. And so now let us make one more step. So this is 1 over alpha e to the power of alpha x, and here we have sine of beta x. And here minus beta over alpha, and here again we integrate this by parts, so it's going to be uv, and again v is 1 over alpha e to the power alpha x, and u is just the cosine of beta x. And here we're going to have minus the integral of, again, v, so it's 1 over alpha e to the power of alpha x, and times u prime, so it's going to be, again, here beta. And this is the derivative of the cosine is minus the sine of beta x, and times the beta appears here, right? The derivative of cosine is minus sine, and the internal derivative of beta, I put it over here. And for the minus sign, we'll just add a plus here. And this is the x, and we'll close the brackets. And now we see that we have the identity that I equals, so let me put it upwards. This is our original integral, so it's 1 over alpha e to the power of alpha x sine of beta x, and here minus beta over alpha squared e to the power of alpha x cosine of beta x, and here we have minus beta over alpha all of it squared, and this is our original integral times I, right? And then, yeah, we've basically solved the integral. Now, what we need to do is to solve the equation for I that we obtained here. So this means that I transfer it to this side. So we're going to have 1 plus beta over alpha squared times I. is, and what we have here. So let's do a common denominator here. So it's going to be alpha e to the power of alpha x. I basically extended by alpha, so it's going to be like the common denominator here is alpha squared. So you know what? I'll just multiply by alpha squared both sides. So I'm going to have here, alpha e to the alpha x sine of beta x, and here I would subtract beta e to the alpha x cosine of beta x. And now when I multiply this by alpha squared here, I get alpha squared plus beta squared. So what I get here is that I equals to, what we're going to have here is 1 over alpha squared plus beta squared. And here we're going to have e to the alpha x. And here we're going to have alpha sine of beta x minus beta cosine of beta x. Right, and then, right, this is it. So this is the bracket. So basically we've done the common denominator and then we divided by this, and that's the solution. That's this integral. And knowing the value of I, now we could actually substitute it and plug it into the step that we had here, right? If we plug in the value for I to this step, we can compute the companion integral, one step less. But I wanted to show you the easy way. But the easy way, you know, it's in mathematics there is a law, just not like a formal law that you have in physics, but one of my lecturers called it the law of conservation of hardness. And what does this mean? This means that how hard a problem is an invariant. And so you can solve a problem in a hard way, or you can solve it in an easier way using more advanced theory. So that's the law of conservation of hardness. And what I mean by this, so if you're familiar with my channel, you know that I really love complex analysis and complex function theory and the Euler formula. So now, if we were to compute this integral again, but instead of sine of beta x, we would use the Euler formula. So we would write the sine of x as e to the power of beta x minus e to the minus I beta x. And here it's basically divided by 2i. And that's the integral that we need to compute. Now, in complex function theory, everything just works the same in terms of integration. And so what we need to compute is 1 over 2i. And basically, this integral becomes immediate because we need to integrate e to the power of alpha plus I beta x. And here minus e to alpha minus I beta x. And note that the powers here of e, if this is z, then this is the complex conjugate of that. And of course, alpha and beta are real here. So notice the symmetry, and it also gives us a clue why this cosine function, the companion, is supposed to appear. And now this integral is immediate because nothing, there are few things in the world that are easier than integration of the exponent. So the integral of this function is going to be e to the power of alpha plus I beta x, all of it divided by alpha plus I beta. And here it's basically the same. It's e to the alpha minus I beta and all it x divided by alpha minus I beta x. No, not x, sorry. Alpha minus I beta here. And this is x. And 1 over 2i, and this is it. This is the integral. Now, if we want to write this to arrive to the previously familiar form, then what we need to do here is, of course, we can take out of the equation e to the power of alpha x, and then over to I. And then here we're going to have e to the I beta, and let's do the common denominator. So I need to multiply it by alpha minus I beta, and I need to subtract alpha plus I beta times e to the minus I beta x, of course, minus I beta x here. And all of it, of course, now the common denominator is number times its complex conjugate. So, right, you know, so if we have z times the complex conjugate of that, this is just the absolute value of z squared, right? So a plus ib times a minus ib is just always a squared plus b squared for a and b that are real. So what we have here is alpha squared plus beta squared. And you see that we're already getting something familiar to what we had previously. And so now we'll have this e to the power of alpha x, and here we have it alpha squared plus beta squared. And let's see what is the coefficient of, so 1 over 2i here that we have. So let's see the coefficient. So here we have alpha e to the I beta x, right? This is the alpha from here, and minus e to the minus I beta x. And all of it, of course, divided by 2i. And this is exactly the sine of I beta. And let's continue forward here. And so what we have here with the beta is that, and here let's write it as minus. So we're going to have I beta here, I beta, and with the minus, so we'll just do it, so it's going to be plus. So I to the e to the I beta x. And here, this is this one, and this one is going to be with the, so it's with the minus again, so it's minus minus for this plus, so it's actually has to be a plus, so it's going to be plus beta e to the I beta x, right? This is this, and we basically need to divide by 2i here, and notice that the I is getting reduced here. And all in all, what we get is the previous expression, so it's e to the power of alpha x, and here alpha squared plus beta squared. And here, this is exactly the Euler formula for alpha sine of beta x. And here we have the Euler formula for minus beta, the cosine of beta x. And of course, for the first time in my video stream, I forgot plus a constant. And I forgot plus a constant here. Yeah, plus a constant. So it's the same result. So I hope that you enjoyed this video. So we've seen 2 ways to compute this integral. I hope you enjoyed it, and please consider subscribing if you liked the content. Thank you for watching.